In this video, we'll look at how to sketch the curve of a parabola using derivatives. So the parabola given is f of x equals x squared plus 4x minus 12. The first thing we want to do is find the zeros. Well, we know the zeros occur where x squared plus 4x minus 12, that is the function, equals 0. And we can find that by factoring. What multiplies to negative 12 and adds to 4? If you're not sure what I'm doing right now, you can watch the video on factoring using Bergman technique. The numbers I need are 6 and negative 2. So that means we can factor this to x plus 6, x minus 2. In other words, there's a 0 at x is negative 6 and x equals 2. That's our zeros. Okay, got our zeros. Now we want to look for max or min points. Max or min points occur where the function's derivative, that is f prime at x, equals 0. So let's take the derivative of this function. The derivative is just x squared becomes 2x, and 4x becomes plus 4. The derivative of negative 12 is nothing. And again, there are videos on how to do derivatives, particularly this power rule or polynomial that I just took the derivative of. You can watch those videos. Nevertheless, I'm going to solve here by bringing the 4 over, or subtract 4 both sides, and divide by 2. I get x equals negative 2. That's where there'll be a max or min. The last thing we want to do is check for our inflection points. Where is there a point of inflection? That'll occur where the second derivative equals 0. So let's take the derivative of the derivative, that is the derivative of 2x plus 4. Well, the derivative of 2x is just 2. The derivative of 4 is nothing. So we get 2 equals 0. But of course that's a mathematical impossibility. So we put a slash equals saying that can't be true. Therefore there's no inflection points. But we do have some other points to look at. And now that we've checked all three, the zeros, the max mins, and the inflection points, we're going to make a table. That is, we'll look at x, and f at x, and f prime at that x, and f double prime, or the second derivative, at that value as well. And we're going to see what that can tell us. So I'm setting up my table here, and there's three spots I want to look at. The first spot was at x equals negative 6. I'm going to go in order from lowest number, negative 6, and then my next number is x is negative 2, and then my last number, x equals 2. And I want to know what's f at x at those values. Well, pretty easy to know what f at x is at negative 6 because it's a 0. And so by definition of a 0, f at x at negative 6 and at positive 2 will both be 0. But I also want to know what f at x is at negative 2, so I'll need my calculator. You can sub it into either of these equations. I'd probably sub it in here. I think it'll be faster. That is, it's going to be negative 2. In fact, I can probably do this without a calculator. Sub in negative 2 here. I get negative 2 plus 6 is 4. And here I get negative 2 minus 2 is negative 4. So what's negative 4 times positive 4? You get negative 16. Okay, didn't need a calculator. What's f prime at x? Well, I can sub in f prime at negative 6, so sub negative 6 in here. I get negative 6 times 2 is negative 12, plus 4, I get negative 8. And then if I sub in negative 2, well, that one's easy. For negative 2, that's the max min. It's exactly where it equaled 0. And if I sub in positive 2, what's 2 times 2 plus 4? Just 8. And then finally, what's f double prime at x, or what's the second derivative? No matter what, the second derivative equals 2. So what does all that mean? Well, the f at x values tell us a point. It tells us at this x, here's the y. At this x, here's the y. At this x, here's the y. The f prime at x values tell us at x equals negative 6, this is sloping downwards. At negative 2, the slope is 0. It's a flat slope, a turning point. And at x equals 2, the slope is sloping upwards. What does this second derivative of continuous 2's tell us? It tells us that at all points it has to be concave up. It has to look like this shape. And you might note that at this point here it'll go up forever on the left, and at this point here it'll go up forever on the right. And now we have enough information to sketch the graph. So let's draw the y-axis and label it with arrows and a letter. Same thing for the x-axis. And for our x scale, you don't need to label it super precisely, but if -6 is out here, then -2 will be about out here, then 2 will be about here. And you can use a different scale on your x-axis than on your y-axis. So maybe this is a height of 10, and this is a height of, say, -10. So what do we know? Well, we know our zeros here at -6 and at 2. And we know that at -2, you're at your lowest point, your turning point of -16. So somewhere down here, let's label that point. -2, -16. And at that point, it's going to be a flat rate of change. But the whole time, this function is concave up. So I look one at a time and see what's happening. At x equals -6, here's my 0. But my slope should be negative, so I'm going down. And my concavity, same thing, should be facing concave up. Good. And I get to my spot here at -2. I'm down at -16. I'm flat in terms of the steepness of my tangent or my slope, but I'm still concave up. And then I make my way concave up towards my next point, 2. At this point, my slope should be positive. It is. And I'm concave up, and I'm going to finish this way. Put arrows on my graph. And I've got it. There's a sketch of a curve, of a parabola in this case, using its derivatives.